In this video, we're going to introduce a simulation-based method for inference, or more specifically, for constructing confidence intervals called bootstrapping. We're going to define bootstrapping, and then we're going to use it to estimate a parameter other than the mean to highlight the versatility of the method. Lastly, we're going to discuss its limitations as well. We have a data set of 20 apartments randomly selected from Craigslist housing ads. These are apartments with at least one bedroom in Durham, North Carolina, where Duke University is located. First, let's take a look at the distribution of these rents and think about, is the mean or the median a better measure of typical rent in Durham? The median should indeed be a better measure here because the distribution of rents are right-skewed. The next question is, can we apply central limit theorem-based methods we have learned so far to construct confidence intervals for the median? And the answer is no. So a new method is indeed needed here. The term bootstrapping comes from the phrase of pulling oneself up by one's bootstraps, which is a metaphor for accomplishing an impossible task without any outside help. In this case, the impossible task is estimating the population parameter, that unknown population median, using data from only the given sample. Note that this is something we've already been doing. In fact, it is what statistical inference is all about. We have a sample, and we use that sample to make inferences about the unknown population. So here's our original sample of 20 apartments, and the rent amount for each apartment is shown here as well. The sample median is $887. In bootstrapping, we assume that for each observation in the sample, there may be others like it in the population. So we can think of our bootstrap population as a population where each observation from the sample appears many times. And then we take samples from this population to get an idea of how medians from the original population would look like if we actually could take samples from it. So how does this work in practice? We don't actually create the bootstrap population, but we simulate it by taking many samples from the original sample with replacement. So step one, take a bootstrap sample. This is a random sample taking with replacement from the original sample, the same size as the original sample. Step two, calculate the bootstrap statistic. This is whatever statistic you're interested in. In the example, we were interested in the median, but it could be a mean, a proportion, a standard deviation, or whatever you like. Then we repeat these steps 1 and 2 and create the bootstrap distribution. This is a distribution of bootstrap statistics. This should feel familiar. It's actually just like creating the sampling distribution, but where there's one big difference. We're taking samples from the original sample instead of from the population to which we don't have access. Here's our bootstrap distribution of medians, constructed based on 500 simulations. So each one of these dots represents a median from a bootstrap sample. And remember, each bootstrap sample is a sample taken with replacement from the original sample of the same size as the original sample. It's really important to understand what with replacement means in this context, as well as the purpose it serves. So say I have a bag in my hand with 20 cards in it, each card showing the rent for one of the apartments in my original sample. Taking a bootstrap sample from this bag means grabbing a card and noting the rent on the card and then putting that card back into the bag. In other words, replacing the card before selecting the next one. So that first card, that apartment, becomes a candidate for the second row as well. So suppose that was an apartment with rent of $733 in my sample. Putting it back in the bag means that I'm assuming there could be others like it in the population, so it would be conceivable to get others like it in a sample if I had access to the original population. Taking a bootstrap sample means doing this 20 times with replacement, and because we're sampling with replacement, each sample is going to be slightly different than the other, yielding a slightly different sample statistic. If we didn't do this with replacement, then we would end up with the same sample over and over and the same median over and over. Using the bootstrap distribution, we can calculate a confidence interval in 2 ways. The first is the percentile method, where we estimate, say, a 95% confidence interval simply as the middle 95% of the bootstrap distribution. So the bounds of the interval are the 2.5th and the 97.5th percentiles of the bootstrap distribution. Another and more accurate method is the standard error method. Here we calculate the interval as the sample statistic plus or minus t star times the standard error of the bootstrap distribution. And the critical t-score will have n minus 1 as its degrees of freedom, where n is the original sample size. This dot plot shows the distribution of medians of 100 bootstrap samples from the original sample. We want to estimate the 90% bootstrap confidence interval for the median rent based on this bootstrap distribution using first the percentile method. So the middle 90% of the distribution is 90 observations in the center. Then we're going to have only 10 left for the tails, meaning 5 on each side. Counting off the dots from both sides, the confidence interval comes out to be roughly $740 to $1,050. Note that 100 is an awfully small number of simulations. We would usually use 10,000 or so, and of course we would use computation to create these bootstrap distributions, not sampling from an actual bag. We used 100 here just to make it easier to count the dots for illustrative purposes. Now let's take a look at the same distribution again, and this time construct an interval using the standard error method. This would be calculated as the sample median plus or minus t star times the standard error of the bootstrap distribution, which we're given. The sample median was 887, plus or minus 1.66 for t star times 89.5758 for the standard error, yielding a confidence interval of approximately $738 to $1,036. So we're 90% confident that the median rent in Durham is somewhere in between these. So putting these together, we can see that the percentile method and the standard error methods yielded intervals that are pretty close to each other, even though they're not exactly the same. Bootstrap intervals do not have as rigid conditions as on sample size and skew as central limit theorem-based methods. However, they will yield more accurate estimate if the sample size is larger, just like any other method. If the bootstrap distribution is extremely skewed or sparse, the bootstrap interval might be quite unreliable. And finally, whatever method we use, simulation-based or central limit theorem-based, we still need a good representative sample from the population. Simulation-based methods are not a cure for bad samples. If your sample is bad, your estimates will be bad. It's garbage in, garbage out. Since bootstrapping the process sounds a lot like the process we described for building sampling distributions, let's take a moment to compare and contrast bootstrap and sampling distributions before we wrap up this video. Sampling distributions are created using sampling with replacement from the population. Bootstrap distributions are created using sampling with replacement from the sample. And both of these distributions are distributions of sample statistics.